Welcome to the fourth lecture video for our Class 3 time series of lecture videos. We're continuing in our discussion of reactions of conjugate dienes. We've reached point B, reaction of conjugate dienes with diatomic halides. So here we've got our 1,3-butadiene. We throw in bromine in dichloromethane, 25 degrees C, room temperature-ish. And again, we can get 1,2 addition or 1,4 addition. Under these conditions, the majority of our product, 88%, is 1,4 addition as a mixture of cis and trans alkenes. And we get about 12% of the 1,2 addition, which is racemic. In terms of mechanism, we're not really sure what's going on here. So I've drawn you a possible mechanism. We could form one of those cyclopropylbromonium cation intermediates, which gets opened up by bromide, or we could simply form an allylic cation. Nobody really knows. So we've drawn just forming an allylic cation, which could be substituted by bromide, or again, we consider resonance, which we all know is a lie. It's really, an allylic system, molecular orbital system, and our nucleophile can attack either of the terminal carbons of our allylic system. Of course, it looks like room temperature in dichloromethane is a thermodynamically controlled reaction, as we favor the thermodynamic product versus a kinetically controlled reaction. Point C, the Diels-Alder reaction for dienes. This is a really interesting reaction. It motivates a lot of people to become organic chemists, although there are a declining number of jobs for us, at least in this country, unless you want to end up teaching, which is a fairly safe way to practice this art. Pharma and medicinal chemistry, it's very difficult to land a job there. Let's see. So here we've got a diene and an alkene or an alkyne, and we go to a cyclohexene compound, or in the case of using the alkyne with the diene, we go to a cyclohexadiene compound. So what am I saying? Well, diene, alkene, we get them together, we do these three arrows, and we get a cyclohexene product. This is kind of an interesting reaction, right? It's also called a 4+2 cycloaddition. One thing you'll notice about it is, in terms of entropy, we're bringing two molecules together to form one. So we're decreasing entropy, right? Delta G equals delta H minus T delta S, and the change in entropy is a minus. So minus T times a minus is a plus, right? So the enthalpy of reaction we'll discuss in a little more detail in a future reaction, but suffice it to say that it's negative. But at some temperature that's high enough, that minus T delta S positive term becomes positive enough that delta G will go to 0. And you can think about doing a retro Diels-Alder, which has actually been applied and shown to be useful in synthetic approaches to molecules. So, with that, we'll go ahead and discuss a few examples before we call it a day on this video. One, for good reactions, use an electron-rich diene. So here we've got 2,3-dimethyl-1,3-butadiene and an electron-poor alkene. Here we've got a trifluoropropene, or trifluoromethyl ethylene, whichever way you want to call it. We can react those with our magic 3 double-headed arrow pushing mechanism, and we can get this cyclohexene in a racemic form. We've got a stereocenter there. We'll talk more about regiochemical outcomes and stereochemical outcomes in a later video. It's kind of interesting stuff. The alkene is electron poor by what? Inductive effect. We've got all these highly electronegative fluorines that suck electron density out of the carbon, which then pulls it out of the carbons that form the pi bond. Here's another example. Here we've got 1,3-butadiene, and here we have a methyl ester group, which is, a pretty electron withdrawn carbon, right? Carbon's essentially got 3 bonds to oxygen. One of them is a double bond, right? And another is a single bond. At any rate, we can do a 4+2 and end up with this racemic cyclohexene. You can definitely see that the alkene is electron poor by resonance, which we all know is not real. But hey, you can draw some resonance form where you've got a formal positive in the 2-carbon system that makes up your alkene, which is kind of neat. All right, last example, and then we'll, I don't know, maybe we should just finish this class time series of videos with this video. It's a little much, 6 minutes. We are flagging in our attention probably already. Oh, look, it's an alkyne. In fact, one that has 2 trifluoromethyl groups attached to it, so it's a very electron withdrawn alkyne that can also react with these dienes in a 4+2 sort of reaction system. And here we get a cyclohexadiene, right? Non-conjugated diene, but that's our product. So alkynes can serve as dienophiles as well. They love dienes, right? Dienophile. I think we'll go ahead and call it quits for this reaction video. In the next one, we'll discuss how the Diels-Alder reaction is concerted. That means in the transition state, the bonds are formed and broken at the same time, like everything playing in concert. So we'll start there next. See you soon.